Video number 2. So this is just polishing off chapter, I want to say 9, because I think we decided to move on from this because we didn't know how to differentiate trig functions, basically. Okay, so we should know everything in there, that acceleration is the derivative of velocity, and it's the second derivative of displacement. So we've got a ball moving with the displacement function like that. So this is in one dimension basically because it's just x and t. So it's on like the x-axis and it's just doing something like this, right? In reality, it's probably doing something like vertical movement, it's bouncing, right? But you know. So find the velocity function and the acceleration function and then sketch the acceleration function. So I don't know why I wrote acceleration and gravity there, but we'll just get rid of that because that's not quite right. So first thing I'm going to do is just expand this to help me with differentiating because I don't want to use the product rule. Do I, Charlotte? Now Charlotte's wondering, why did I pick on her? No reason. So there's the velocity function, x dot. And then the acceleration function is x double dot. Oh, maybe this is why I wrote acceleration is minus 10 is gravity. So that gives you a bit of a hint that it is a ball bouncing and dropping. Okay, and sketch the acceleration function. Okay, it's not particularly interesting, but here's the acceleration, here's time, and here's the function at minus 10. Notice I started there at the vertical axis just because time can't really be negative ever in these questions. Doesn't make sense. So find and describe displacement, velocity, and acceleration when t equals 2. So t equals 2, let's just map them all out. So x equals 80 minus 5 times 4, which is 20, so that's 60. So its position is 60 meters or whatever above the ground, you would think. X dot velocity is 40 minus 40, so 0. So it's still, it's not actually moving, it's at a stationary point. So that probably means if you actually thought about the ball bouncing, it probably means that it bounced up and it had stopped. Oh, oops, sorry. So velocity is positive, so it's heading up, okay. So it might be here. So t equals 4, it turns out would have been the top of the motion because velocity was 0, and then x double dot is always minus 10. So it's going up, being pulled down. So it's slowing, right? So it's like you're driving your car and you're moving forwards, but you're applying the brakes. So you've got a negative acceleration force, which is braking, but you're still moving forwards, you're just slowing over time. Okay. So when is the ball speeding up and when is it slowing down? What? The ball is never speeding up. Doesn't make sense. The ball is always slowing down because velocity is the velocity function. So velocity is always decreasing, so it's always slowing down. So decreasing, which mathematically we read as the second derivative, or the derivative of the thing we're talking about, is negative. So it's always slowing down. So the question is bunk. As it seems to be the case in a lot of these textbook questions, Okay, next one. In work example 5, we examine this function, find the acceleration, and when the acceleration is 0. Okay, so x dot is 3t squared minus 12t plus 7. X double dot is 6t minus 12. Set it equal to 0. T must be 2. Where is the particle this time? So x is oh man. So plus 30 plus 12. What's that? 2 2/3. So 14 2/3. So 12 minus 12, 15. So its displacement is 14 2/3 meters to the right. Its velocity is 15 meters per second, so it's moving forwards. And its acceleration is 0, meaning its velocity is not changing at that point in time. It's still moving, but its velocity is not changing. If it were not moving, that would mean velocity was 0, x dot. Next one, yeah, this is why we stopped, right? So I think I asked you to do this yourselves, didn't I? Oh well, here we go. So we've got a particle with that displacement function. Find its velocity and acceleration. So x dot, derivative of sine is cos, so 2 pi cos t. X dot is negative 2 pi squared times sine pi t. So graph all three functions in that time interval. All right, so the period of the function is 2, hence the domain we've been given. Okay. So here's 2, here's 2 pi, here's 2 pi squared, roughly. So I'll do x in blue. So that's 2 sine pi t. Here's 2. So we just do something like this. There's 1. I will do x dot in green. So that's 2 pi cos. So we start up here. Like that. And then I'll do x double dot in red. So that's minus 2 pi squared sine. So it's something like this. Whoop, pretend I got back to there. Okay. I'm not going to mark in the troughs. Okay, but that should be 2 pi squared. Okay, so when is it at the origin? Well, clearly from my diagram, that's at t equals 1. Oh, sorry, 0, 1, and 2. So all the times it passes through the vertical axis, the horizontal axis. And find its speed and acceleration at those times. So t equals 0. Well, let's just do a little table. So here are my t values. Here's my x dot, here's my x double dot. 0, 1, 2. So we could look at the diagram for this. So an x is 0, the velocity is 2 pi, and the acceleration is 0. Right, I'm just looking at the green curves and the red curves over here. When t equals 1, the acceleration should be minus 2 pi, and the velocity should have been 0. I should have passed through here. You've probably been annoyed at that this whole time. And then we get 2 pi and 0 there as well. Okay, so it turns out that when it's passing through the origin, it's also not accelerating. find all the times when the particle is stationary. So that's when x dot equals 0, which is here and here, and that should be basically at a half and at 1.5. Because it should be halfway between the other things, because it's cos versus sine. And then we can do the same thing again. So its position is 2, its acceleration is minus 2 pi squared, its position is minus 2, its acceleration is 2 pi squared. So when it's stationary is actually its greatest acceleration and its furthest position, because it's always being, that's where it's turning around. Okay, so when its acceleration is 0, it's basically going out here, turning around and coming back, out here, turning around and coming back, out here, turning around. So this is when the velocity is 0 at all these points. It's where its position is its furthest out and the acceleration is pulling it back in as heavily as possible. Okay, so basically what's happening in this is the acceleration, which is the red one, is always acting directly opposite to its position, right? So as it's going out, it's always being pulled back in. So you can maybe think about it as like some toy where you've got a stick and attached to that stick is some kind of a, I don't know, a rubber band or something with a ball on the end. And as you hit the ball out, it's moving forwards, but the rubber band is always trying to pull it back in. Okay, and eventually it gets to a certain distance out where the rubber band stops it and the rubber band is stretched out as much as possible, and so the force pulling it back in is its greatest. So that's a description of the motion, I suppose. But the main thing to note is that the acceleration is always directly opposite to its position, so it's always being pulled back to the center, right? So I would say always being pulled back to the center, proportional to distance from the center, basically. I mean, the word proportional is a bit dangerous in maths, but let's just leave it there. Okay, particle is moving, so its height, x blah, 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 blah. Okay. Find the velocity and acceleration functions. I just want to draw the looks like this basically. When t equals 0, x equals 1, so it looks like that. So x dot is positive 3 e to the minus t, 3t, sorry. X double dot is minus 9 e to the minus 3t. So this is always positive and this is always negative. So the velocity curve looks like this, basically. Passing through 1 and approaching the axis, never hitting it. So all these points are going to go through 1 there. Let's pretend I'm actually good at drawing. And then the acceleration function looks something like that. Okay, well they're pretty obvious from the diagram. They are 1, 1, and minus 9. Oh, sorry, that should have been 3. Oh, jeez. Way to not correct me. Oh, man. Sorry. Whee. So position tends to 2, acceleration tends to 0, and so does velocity. So briefly describe the motion. So it starts at 1, heads to 2, always moving forward, and always getting slower. So moving forward, heading to 2, slowing, always. Okay, I'll stop there. Here's some questions to complete.